Hi, this video describes binary trees. Binary trees are a data structure that's kind of a stepping stone to binary search trees, which we're going to get into very soon. Before we get into binary nodes and binary trees, let's review doubly linked list nodes because they're similar to binary tree nodes. In a doubly linked list, every element is stored in a node. So for every single element in the list, we create a node object. That node object has one element. In my sketch, it's the integer 4. Every node has a previous pointer, which we draw as a left pointing arrow, and every node has a next pointer, which we visualize as a right pointing arrow. And there would be some incoming edges, which I drew in gray here, but those are not part of this node object. Those belong to other objects. We visualize a collection of these nodes as a horizontal line. The computer doesn't actually know about that. The computer just sees these as memory locations, but the way that we imagine a doubly linked list is as a horizontal line left to right of these nodes. A binary node is kind of similar, it just has a little bit more going on. So a binary node has one piece of information from a map. In our map, every element is a pair, and the pair has a key and a value. So every binary node has that, one pair of one key and one value. A binary node has a left child pointer, as it's called, that kind of goes left and down, and a right child pointer that kind of goes to the right and down. A binary node has a third pointer called a parent pointer that points upwards. One of these pointers can be null if there's nothing there, just like with linked lists. Eventually you get to the end of a list and we can use null to mean you've reached the end of the list. Similarly, eventually you get to the top of the tree or the bottom of a tree and we use null to represent that there's nothing left. We call an edge the two pointers that connect a pair of nodes. So between this 7 node and this 1 node, there would be 2 pointers. The 7's left child pointer would point at the 1, and the 1's parent pointer would point up at the 7. So there's actually 2 pointers between here, one going down and one going up. We use the word edge to refer to that connection which involves 2 pointers that have to be kept synchronized together properly. The way that we sketch a node is as an oval or a circle. We draw the key on the inside of that oval or circle. There's a convention that we don't draw the values in. Every one of these nodes would contain a key value pair, so maybe 7 is associated with a string, but just to keep this concise and not be too time consuming to sketch, we only draw the keys and we don't draw the values. And we also draw the edges as a straight line segment with no arrowheads. Even though this is 2 pointers, one going up and one going down, for simplicity and to speed up the drawing process, because these trees have a lot of edges, we just draw it as a straight line segment. So just to kind of recap how the pointers work, 1, for example, has a left child pointer pointing at the 8 node. 1's parent pointer would point up at the 7 node. 7's left child pointer points down at the 1 node. 7's right child pointer points down at the 4 node. 7's parent pointer would be null because there's nothing above 7. And 8's child pointers, both of them would be null because there's nothing below 8. 1's left child pointer points at 8. 1's right child pointer points at null because there's no right child of 1. And we don't draw these null pointer edges. So even though there is a pointer in the 7 node pointing up at null, we don't draw it because, again, these node collections have quite a lot of these null pointers and it just gets kind of tedious and cluttered to draw all of them in. Now that we've defined an individual node, we can define a binary tree. A binary tree is a collection of these nodes that are organized in a certain way. A binary tree has 2 data members. One is a root pointer to the topmost binary node. So over here, I've sketched a binary tree, and root is a pointer, and I'm drawing an arrow down to the 7 node, which is the topmost node. And a tree could be empty, in which case the root would point at null. We also have an int size to keep track of the number of elements so that we can report the size of the tree in constant time. We visualize one of these trees as kind of a family tree shape, this kind of branching out diagram, and we visualize this and sketch it with a child pointer moving down a level. So 7 has 2 children, 1 and 4. They are drawn below 7, down a level in the sketch. And likewise, a parent pointer following a parent pointer moves us up in the sketch. So 1's parent is 7, so 7 is drawn above the 1. Okay, there's a bunch of terminology for these nodes and trees. This is an important data structure in computer science. It's used in a lot of ways. We have a lot to say about how these trees work, so we have a bunch of terminology to make that easier. It's kind of a mixed metaphor, I have to admit. There's kind of 3 different perspectives we have on this that comes up with 3 sets of terminology that don't mix perfectly. There's kind of some family tree stuff, children and parents. There's some arboreal tree stuff. That means having to do with trees, the plants, woods, and some altitude, higher or lower kind of stuff. So this slide is the family tree-based terminology. So the parent of node X is the node directly above X that you get to if you follow the parent pointer. So 1's parent is 7, 8's parent is 1. The child of a node is one of the nodes directly below that node following left or right child pointers. So for example, 7's left child is 1, 7's right child is 4. 7 has 2 children, 1 and 4. The ancestor of node X is either X or any node on the path from X up to the root. This is using the family tree kind of a thing. So 8's ancestors would be 8, 1, and 7. This kind of follows the family tree thing. If this was a family tree, X would be a grandchild, 7 would be a grandparent. And so 8's ancestors would be 8 counts itself for some technical reasons. 1 would be 8's parent, 7 would be 8's grandparent. So ancestors are what you get when you go upward toward the root. Descendants are what you get when you go downward toward the bottom. So descendants of node X are X itself, and any of X's children or any of their children or so on moving downward in the tree. So 1's descendants would be 1 itself and also 8. 7's descendants would be all of 4 nodes here because all nodes descend from 7 in this sketch. There's some other terminology that follows from arboreal trees. Again, arboreal has to do with plant trees that are in forests. And the analogy works with an upside down arboreal tree. So we use this to describe some of the shapes in a binary tree. This is what a tree looks like in real life. The trunk of the tree is at the bottom and the leaves are at the top. But actually the way we use the terminology is as if this is flipped upside down. So the root is the topmost node, and that corresponds to how a upside down arboreal tree would work. The root is underground, so it's very high in this upside down picture. So the root is 7 in this example. All nodes are descendants from the root based on how descendant is defined, and the root has no ancestors aside from itself. Every node counts as its own ancestor, but there's no other nodes that are ancestors of 7 because it's at the top. A leaf is at the bottom. So in a real arboreal tree, the leaves would be, at high tips of the branches of the tree, but since we flipped it upside down, the leaves are kind of at the bottom. They're the border between the tree and the nothingness below them. So a leaf node is a node with no children at all. So 8 is a leaf and 4 is a leaf because there's no nodes below 8 or 4. So the leaf nodes are kind of the bottom of the tree. There's nowhere else to go below the leaves. A leaf has no descendants besides itself. 8 has no descendants other than 8. 4 has no descendants other than 4. Finally, there's one more category of this terminology, which has to do with altitudes or how high or low you are in the tree. One is called depth. Depth is based on how deep you are kind of digging down from the root. So the depth of node X is the number of edges between X and the root. So for example, 8 is down here. 8 is at depth 2 because to get from the 8 back up to the root, I need to follow one edge right here and a second edge. So depth is 2 for 8. The root has depth 0 because if you start at the root, you're already there. You don't need to follow any edges to get to the root. So I'm going to draw these in on my example. I'm going to put the depth number to the left of a node and it's drawn in red. So 8 has depth 2 because it takes 2 steps to get to the root. One node has depth 1 because it takes 1 step to get to the root. 4 is also at depth 0 and the root is always at depth 0. The height of node X is going from the bottom, how high you are kind of off the ground or how far you are from a leaf. So the way it's defined is it's the maximum number of edges between node X and a leaf. We have to use maximum because there could be different heights depending on which leaf you look at, right? So when we're talking about depth depth is always anchored to the root. There's no ambiguity about which node we're counting the distance of. But when we go downward from a high node down to a bottom one, there's different lengths. Like 7 could get to a leaf with 2 hops down to 8, or 7 could get to a leaf with 1 hop down to 4. So which one should it be? The way that we define it is it's the maximum of those. So a leaf itself has height 0. 8 and 4 are leaves. They would be at height 0. And for the other nodes, the height is the maximum number of steps it takes to get from that node to a leaf. The height of the entire tree is the height of the root node. So sometimes we say the height of a node, and that's defined as that maximum path length. The height of a tree, the entire tree, is whatever the height of the root node is. So I'm going to draw those in on my example here. I'm drawing the height numbers to the right of each node in blue. 8 and 4 are leaves, their height is 0. 1 node is at height 1 because it takes 1 edge to get to the deepest leaf. And the root node's height is 2 because the longest path to a leaf is length 2. And that means the height of the entire tree as a whole thing is 2.